Today we will be talking about how to use the finite state machine algorithm as a solution for string matching. We will discuss the following topics. What is string matching? What is a finite state machine? How can FSMs be used as string matches? How can FSMs be used as regular expression matches? And what is the algorithm and how does it work? I'm going to go over some examples on string matching and regular expression matching, and then we'll discuss the time complexity of the algorithm. String matching is the task of locating the occurrences of some substring P within some larger input string T. The general string matching algorithm has the following format. String match TP produces array I. Here T is the large input string and P is the substring that we are trying to locate within T. The algorithm returns array I, which contains all of the indexes within T where P occurs. In example 1, T equals string match and P is ring. Ring occurs only once within string match, hence I only contains one element. Note that the value stored is the index of the final character of the substring. In example 2, T equals banana and P equals Anne. Here there are two occurrences of P within T, hence I holds two values. In example 3, T equals Alex and P equals Anne. Although the two do have common characters, P is not found in T in its entirety, hence there is no match and I holds no values. A finite state machine is a mathematical model of computation which is the basis of sequential logic circuits in computer chips. Generally, they are made up of a set of states which are reached depending on the inputs to the machine which has been seen so far. As a string matcher, the input is string T and is fed in from first to last character. Substring P determines the transition function of the machine. Finite state machines are formally defined as Q, Q0, A, sigma, and delta. Q is the finite set of states which the machine can be in. Arrival at a given state depends on the input seen so far and the transition function of the machine. Q0 is the state that the machine begins computation at and is known as the start state. This state may be visited again if the transition function allows it, and Q0 is always a member of Q. A is the finite set of accept states. Arrival at an accept state has different meanings depending on the FSM's use. As a string matcher, the machine arrives at an accept state when substring P has been found within T. A is a subset of Q. Sigma is the input alphabet, and is the set of possible input characters to the machine. As a string matcher, sigma typically contains the 128 ASCII characters. Delta is the transition function of the machine and is determined by P when used for string matching. Delta takes the current state and input as input and produces a new state as output. The transition function can be represented both tabularly and graphically. Generally, we want to set sigma as the set of all characters in T and P, and design a transition function which brings the machine to an accept state each time a matching substring is read. Here are some tips on the transition function. There should usually be P plus one states, one start state Q0, and one state for each of the P characters in P. There will be different types of transitions. I like to give them the following names. Idle, this is when we are at the start state and waiting for a character which matches the first character of P, hence we loop at Q0. Forward, this is when the inputted character matches the next character in the substring, hence we can progress towards accept by one state. Back transitions, this is when we are partway through reading a matching substring when a mismatching character appears. Then we must move back to a state which considers this new character and its predecessors as a possible matching substring. This may or may not be Q0. Post accept, this is similar to a back transition but allows for loops. At the accept state, this is when P's alphabet only contains one character and this is the character which is being read. So here's an example. Here P is set to A, and sigma is A and B. Here we have an idle loop at B because we're waiting for an A to be read in a P. Here we have a forward transition at A because this is directly contributing to a matching substring A. Here the back transitions go straight back to the start state. This is when we read a B, and that's because there are no B's in P, hence they can't possibly contribute to a matching substring. And here we have an accept loop at the final accept state, and this is because P's alphabet only contains A's, so we can loop at A because each A at this point will produce a new matching substring. The advantage of using finite state machines over the KMP or BMH algorithm is that finite state machines can be used for regular expression matching as well as string matching. Regular expression matching is similar to string matching, but it accepts when a substring is read which is defined by a given regular expression. Hence there are multiple, often infinite variations of P that could be accepted. This makes regular expression matching impossible for KMP and BMH, as the pre-computation tables required would be infinitely large. The most basic of regular expressions are just single characters. All other regular expressions are built up from simpler ones using the following operators. R equals R1 starred. This is the clean start and it means R is equal to 0 or more repetitions of R1. R equals R1 plus. This means R is equal to 1 or more repetitions of R1. R equals R1 or R2. This means R is equal to R1 or R2 but not both. R equals R1 concatenated with R2. This means R is equal to R1 followed by R2 in that specific order. When it comes to designing the FSM, again we want to set sigma as the set of all possible inputs to the machine. The transition function is what plays the key difference here, and is considerably harder to implement than a simple string matcher. Here are some generalities about the implementation of the transition function. Regular expressions containing the clean start or the plus operator will involve loops at any required state or group of states. Regular expressions containing the OR operator will involve forward transitions with multiple characters on the edge. Concatenations are easiest to implement and are designed similarly to string matcher FSM concatenations. This is because strings are essentially equal to regular expressions without the clean start plus or OR operator. The algorithm which is used by computers to implement the transition function is quite computationally expensive. It is known as the power set construction. In order to use finite state machine matching in a computer program, we need to put it into algorithmic form. Here is the proposed algorithm. It accepts string t and regular expression r as input. We start here with the initialization. First we set n to be the length of t. This is for use in the for loop down here, where we input t's characters one by one. We then set delta using FSM build, with r as an argument. FSM build likely uses the power set construct. Here delta is some data structure containing information about states and transitions. We then set S, the current state, to 0, signifying that it is the start state. Now we enter the operation of the algorithm. This two-line section occurs once for every character in T as prescribed by this for loop. Here the next state is assigned by calling the function version of delta, with the current state and input as argument. The algorithm then checks if the new state is contained within the set of accepts. If this is the case, output is called with I, the index of the final matching character of the substring, as an argument. Output I takes I and adds it to the end of some data structure for retrieval later. This could be something like an array or linked list. The success of the matching is therefore checked by looking at the data structure containing the indexes. If no indexes are stored, then no successful substrings have been found. If values are stored, this means there have been successes, and these values will give the positions of the successes. Here's an example string match. Note that the numbers here correspond to the numbers here. In line 1, n is set to 6. In line 2, the transition function and the sets q and a are defined. In line 3, the current state is set to 0. For lines 4 and 5, we repeatedly take the current state and input and check if the new state is a member of A. For current state 0 and input A, the next state is state 0. For current state 0 and input A, the next state is state 0. For current state 0 and input B, the next state is state 1. For current state 1 and input A, the next state is state 2. For current state 2 and input B, the next state is state 3, which is a member of A. Therefore we add I equals 5 to the array. For current state 3 and input B, the next state is S1. At this point I is now equal to n, meaning that we have exhausted all input, hence the algorithm terminates. Here's an example regular expression match. At line 1 n is set to 8. At line 2 the transition function is set, as well as the sets q and a. At line 3 the current state is set to 0, meaning that we are at the start state. With current state 0 and input a, the next state is state 1. With current state 1 and input b, the next state is S1. With current state 1 and input a, the next state is S1. With current state 1 and input a, the next state is S1. With current state 1 and input c, the next state is S2, which is a member of A. Therefore we can add I equals 5 to the array. With current state 2 and input d, the next state is S2, which is also a member of A. Therefore we can add I equals 6 to the array. With current state 2 and input A, the next state is S1. With current state S1 and input C, the next state is S2, which is a member of A. Hence we add I equals 8 to the array. I is now equal to n, hence the algorithm terminates. An important consideration for any algorithm is its running time. This table shows how the FSM matcher compares to the Knuth, Morris, Pratt and Boyer-Moore-Horspool algorithm. Here the pre-computation time is the time required for FSM build and depends on the pattern size and the size of the input alphabet. Although the finite state machine algorithm has the highest pre-computation time, it has a very good matching time. Since its matching time is just theta of the size of t, This makes it a very good option for large P, as P does not affect its matching time. The main benefit of FSM over KMP and BMH is its ability to match regular expressions.